Today we'll look into one of the four classical elements in Greek theory. The element which was considered to be the driving force for the birth of the cosmos. Wondering what it is? We'll give you a hint. Well, if you're actually alive, then it's mostly because of this stuff everywhere around you. The stuff without which we might not know life as we know it. The stuff which keeps the living things alive, which allows aircraft to fly and ships to move, which even gives the power to generate electricity. You might have guessed it by now. Yes, it's air. Air is a mixture of several gases held together by Earth's gravity, surrounding the Earth and making up its atmosphere. The percentage of gases making up the atmosphere is different, ranging from the highest percentage by volume of nitrogen, followed by the oxygen that we need. Almost 99.99% of the volume of the atmosphere is occupied by just four gases, namely nitrogen, oxygen, argon, and carbon dioxide. But numerous other gases like neon, helium, krypton, methane, ozone, etc. are also present in very small amounts. All these gases and the air around us has some weight. Due to its weight, the air exerts pressure on any point. But the air is not evenly distributed throughout. At some places, the air is denser, so it exerts more pressure. The pressure and density of air also vary with the height because air at higher altitude is less dense, so it exerts less pressure. For example, a bottle sealed shut at a high altitude will be crushed on coming down due to the increase in pressure at lower altitudes. To generalize the calculation, the mean sea level is taken as the average level of the Earth's water bodies, and altitude is measured with for the level. The atmospheric pressure at mean sea level is approximately 101 kilopascals, also approximated to 1 atmosphere. In most calculations, the pressure is measured as absolute pressure, which is given by the sum of gauge pressure and the atmospheric pressure. Here, the gauge pressure is the pressure measured by an apparatus without considering the atmospheric pressure. Absolute pressure is generally used in calculations because it measures the pressure including the atmospheric pressure. Although hydraulic circuits are better at providing large forces by using pressurized liquids, pneumatic circuits prove to be better because they employ pressurized air in the circuits, and air happens to be safe and readily available. Apart from that, liquids tend to have greater inertia due to their weight and have larger frictional pressure, thus resulting in more power loss. But the pressure, volume, and temperature of gases, such as air, vary largely. During the 16th century, scientists discovered the laws that the gases obey and named them perfect gas laws. All gases have different properties, and therefore, to maintain a standard measurement, these laws were derived for an ideal or perfect gas, and hence the name perfect gas laws. Perfect gases do not exist in reality, but the behavior of real gases as predicted by these laws is quite close. The laws developed relate various parameters, namely pressure, volume, and temperature, and define their relationship. The first law is Boyle's law, which relates the pressure and volume of a gas kept at a constant temperature. This relation between the pressure and volume was first noted by Richard Townley and Henry Power. Robert Boyle confirmed the relation by a simple experiment where he filled a closed J-shaped tube with mercury and concluded after several repetitions of the experiment that, under controlled conditions, the pressure of a gas and its volume had an inversely proportional relationship. The French physicist Edmé Mariotte also discovered the same law independently, and that's why this law is also referred to as Boyle-Mariotte law. The next law, named after the scientist Jacques Charles, is called Charles' law. This law states the directly proportional relationship between the volume of a gas and the temperature. It shows how a volume of a gas increases on increasing the temperature, while a decrease in temperature shows a decrease in volume. For this, the pressure is held constant. We have seen two relations where the temperature and pressure are held constant. Now, for the final Gay-Lussac's law, the volume is held constant. This law relates to the pressure and temperature of a gas. According to Gay-Lussac's law, which is also referred to as Gay-Lussac's law of pressure and temperature, if the volume of a gas is held constant, then the pressure exerted by the gas is directly proportional to the temperature. Now, we have seen the individual relation between pressure, temperature, and volume in the three laws discussed. But wouldn't it be easier if they were all combined into one? Well, all these laws can be combined into what is called a general gas law. This law contains all the three parameters of pressure, volume, and temperature. By keeping one parameter constant, Boyle's law, Charles' law, and Gay-Lussac's law can be obtained. The laws discussed above are crucial in the calculation of various parameters in a pneumatic circuit and are also used in other scientific calculations. But a pneumatic circuit is a lot more than just the compressed air as a working fluid. We will discuss pneumatic circuits and their components in upcoming videos. So stay tuned, and until then, goodbye.